Lecture problem 5. A disk of mass m and radius r rotates around the z-axis with an angular velocity omega 0. A second identical disk, initially not rotating, is dropped on top of the first disk. There is friction between the disks, and eventually they rotate together. The question: what is the angular velocity omega final? Since the disks connected to each other without the interference of a net external torque, therefore the angular momentum is conserved. Net torque equals 0. Therefore the angular momentum initial has to equal the angular momentum final. The angular momentum is moment of inertia times omega, this is for initial, should equal the same quantity after they connected. Before they connected, the angular momentum comes from two disks, 1/2 big M r squared times the omega 0 for disk 1. Notice that the moment of inertia for a disk is a known expression, which is 1/2 mr squared. The other disk was not spinning, therefore its angular momentum is 0. Afterwards, I have two disks combining into one big one, therefore the moment of inertia is going to be 1/2. The mass is twice as much, times the same radius squared times omega final. Notice that this half is a common quantity between the two terms. The r squared here is also going to cancel with this r squared, and also this mass is going to cancel with this mass. What's left? On the left hand side is just omega 0 equals, right hand side I have a 2 here, times omega final. Isolating omega final, we find omega final equals omega 0 divided by 2, which means that the two disks, after the collision, they're going to move slower with an angular velocity half the original one.